Now we also discuss important theorem, but after going to this theorem, we also discuss some example. Well, today we discuss also partial derivative exist and continuous for a continuously differentiable function. Also discuss later, but now we start from one example here. Write if xy equal to x square plus y square. Okay. Xy belongs to b1 0 and take c equal to ab. Take c equal to ab. Then f dash c ab equal to f dash c xy equal to f dash c xy equal to 2x plus 2y multiplied by here 2x 2y here multiplied by 2x a and 2yb. Okay, in this way, and also this one is added because this one is in our product 2xy and 2vy, 2ax and 2vy for all x y belongs to r square. Then what? Then this one, how this one is formed, because f dash c equal to unknown about that here 2x and here 2y. Okay, then this one and here ab, so multiplied by this, then this one is pattern. Okay, then if I here 2a x and y put c, then it's ab. Okay, now it is this portion. I'm going to here. Now mod of if x y difference f of u v equal to mod of x y and difference f of u v equal to how much? There is some problem here. Okay, now this problem is vanished. How this problem created we don't know, but now we start f of x y difference f of u v equal to how much? Equal to, we write here x square plus y square difference u square plus v square. Okay, then this mod equal to how much? X square difference u square and y square difference v square equal to how much? Equal to here x difference u x plus u and y difference v and y plus v. Okay, then how much? This less than equal to norm of mod of x difference u and mod of x plus u and plus y minus v and y plus v. Okay, so now we write mod of x difference u less than equal to norm of x y difference norm of u v and this one, and mod of y difference v less than equal to norm of x y difference u v. Okay, then this less than equal to, then this less than equal to how much? Then this less than equal to, we erase this problem and going to above here. Then this less than equal to norm of x plus u mod of x plus u plus y plus v here, where norm of x y difference u. Okay, then this one is less than equal to, this one less than equal to mod x mod u mod y mod v. Okay, here norm of x y difference u v less than equal to 4 norm of xy difference u. Okay. Now what we obtain here f of xy, we write here norm of f of xy difference f of uv equal to less than equal to 4 difference xy difference uv. Okay, so we do this one. Then we also write continuously differentiable function. Okay, we write here continuously differentiable function. Differentiable function. Okay, let u be an open set. Let u be an open set in Rn, and if u to Rn and if u to Rn be a differentiable function, be a differentiable function, then f dash is a mapping, then f dash is a mapping from u to L Rn Rn. Okay, so f is said to be continuously differentiable. So f is said to be continuously differentiable if f dash is continuous, if f dash is continuous. Okay, now for each x, so f dash is continuous means for each x belongs to u, for each x belongs to u, epsilon greater than 0, there exists delta equal to delta x epsilon greater than 0, such that norm of f dash x difference f dash y norm of L r to the power n r to the power p less than epsilon for all y belongs to u, and norm of x difference y less than delta. Okay, so this one is the definition of continuously differentiable function. Okay, now we're also going to proof of any theorem or is this portion and going to forward discussion about that. Now we write here theorem. Let U be an open set in Rn. U be an open set in Rn. Okay, and let if U to Rn and let if U to Rn be a continuously differentiable function. Be a continuously differentiable function. and then all partial derivatives, partial derivatives del fj by del xi exist and are continuous are continuous for 1 less than equal to I less than equal to n and 1 less than equal to j less than equal to m. Okay, we now discuss proof of this theorem. We write proof here. So the statement says about that if u subset of Rn and if u to Rn be a continuously differentiable function, then all partial derivatives exist and continuous for that. Now we're going to prove of this. Let e1 e2 dot 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 en and e1 dash e2 dash dot 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 em dash be the standard basis of be the standard basis of standard basis of Rn and Rn. R and N are in respectively. Let C belongs to U. Then for U equal to U1, U2 dot 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 UN belongs to Rn and if dash C equal to U1 del F C by del X1 U2 del F C by del X2 dot 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 un del xc by del xn. Okay, now f dash c ei equal to here del of fc by del xi, okay, equal to del f1c by del xi dot 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 del fjc by del xi dot 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 del fmc by del xi. Okay, belongs to Rm. Now we're going to discussion about that. Okay, now we're also going to discussion about that. Hence, hence for hence for 1 less than equal to I less than equal to n, 1 less than equal to j less than equal to m, we get here f dash c ei here is a f dash c ei, not here dot, just multiplication. Here is a dash of inner product equal to fj c by del xi. Okay, then we is this problem, and now going to discussion about that. It is this portion here we write let xy belongs to this U subset of Rn, then del fj del xi of x equal to inner product of f dash x ei here ej dash and del f c by del xi here y equal to inner product of f dash I ej by ej dash. Okay, for all ij. Now let epsilon greater than 0 be given. Now let epsilon greater than 0 be given. Since f dash is continuous, at x, then delta x epsilon greater than 0 such that norm of f dash x difference f dash y L of r to the power n r to the power a less than epsilon for all y belongs to u with norm of x difference y less than delta. Okay, now it is this portion and going to further discussion about that. Here for 1 less than equal to I less than equal to n and 1 less than equal to j less than equal to m, we get del fj by del xi here x difference del fj by del xi here y equal to how much? Equal to here inner product of f dash x ei difference f dash y ei. Okay, and here is a test less than equal to norm of f dash x difference f dash y ei here ej dash. Okay, this less than equal to norm of f dash x difference f dash y norm of ei norm of ej dash. Okay, equal to erase our portion and going to discussion about that. less than norm of f dash x difference f dash y for all y belongs to u with norm of x difference y less than delta. Okay, hence del fj by del xi is continuous at point is continuous at point x for 1 less than equal to I less than equal to n and 1 less than equal to j less than equal to a. Since x is arbitrary, since x is arbitrary, therefore therefore we conclude that we conclude that del fj by del xi is continuous on u is continuous on u. Okay, for 1 less than equal to I less than equal to n, 1 less than equal to j less than equal to n. Okay, so we also discuss stepwise how we handle this one. First, we construct two standard basis of Rn and Rm. Then f dash c u equal to u1 del f cy del x1. Now f dash c ei equal to del f cy del xi. Then this one equal to del f1 c by del xi, not his, and then dot 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 here. Okay, so here f dash c dot 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 ei equal to, then this one happen del f c by del xi, because here one in ith component and others are 0, so just del f c by del xi is here. Then del f c f has m component f1 f2 fm, then this one equal to del f1 by del xi dot 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 del fm by del xi. Then here no, obviously inner product of f dash c ei is a dash equal to del fj by del xi, and then we also let xy belongs to u, then del fj by del xi equal to inner product of f dash x ei and ej dash, and del fj by del xi y equal to f dash y ei ej dash for ij. Let epsilon greater than 0 be given. Since f dash is continuous at x, then this one is happen norm of f dash x difference f dash y l of rn rm less than epsilon for all y belongs to u with norm of x y less than delta. Then obviously we see that norm of del fj xi difference del fj y del xi equal to inner product of f dash x difference f dash y ei ez dash, and then this one less than equal to f norm of f dash x difference f dash y, and this one is less than epsilon since f dash is continuous. Okay, then we also see that del fj by del xi is continuous at point x. So we also prove that partial derivative exists and continuous if f is continuously differentiable function. Okay, that means differentiable of f be continuous, then all partial derivatives are continuous. Okay, now Now we erase this portion and going to further discussion of another important theorem, but now we also not going to this converse theorem. That means how, if all partial derivatives are exist and continuous, then f is differentiable. How this one is happen, but we also not going to this. We now just do one example. One example we do here. Okay, just we see about this theorem. We check here this one is right or wrong. Okay, just we construct here if x y equal to, we write 2x plus 3y. Okay, simple example. Then we know about that this one is obviously continuously differentiable function. Okay, then here, here if we write another one f 2x 3y. Okay, in this way, then this one is, that means f r square to r square, f r square to r square. Okay, then we also show that, here f1 equal to 2x and f2 equal to 3y. Okay, now we also see that del f1 x1 equal to del f1 x1 equal to 2 x1 or del x, and del f1 del y equal to 0, and del f2 by del x equal to 0, and del f2 by del y equal to 3. Okay, then what happened? Then here we also see that here we just 2, here 0, and here 0, here 3. Okay, this one is the, that means require matrix of f dash x y. Okay, then how we, that means how we represent this one. Then obviously we see that, no, here we see that this one are also continuous. That means del fj by del xi, that means del f1 by del x, del f 2 by del x, del f1 by del y, and del f2 by del y are also continuous. Okay, so why continuous? Because f is continuously differentiable. Okay, that means f differentiable is always here continuous. If we here write, that means f dash xy, then this one here xy and 2x plus 3y. Okay, then we also now check here. Okay, check here that these derivatives are also continuous. But if we do one another example, then we also see better. Okay, but if we construct another example, then here we also see that we erase this portion and we also construct another example. if we construct here f of xy equal to x square plus y square here x1, okay, then what happens? Okay, then we also know this one f1 x y equal to x square plus y square and f2 xy equal to x1. Then del f1 by del x equal to 2x and del f1 by del y equal to 2y. Here del f2 by del x equal to y and del f2 by del y equal to x. Okay, then then we also show that f is if f is continuous and differentiable of f equal to how much differentiable matrix of x equal to this one, okay, 2x 2y, yeah, y x, okay, because Jacobian of this equal to this one, okay, that means del f by del x, del f1 by del y, and here del f2 by del x and del f2 by del y. Then we see about that. Here if we dot u, then this one is here if f dash xy dot u, okay, then this one implies 2x 2y yx here u1 u2, then this one is 2x u1 here plus 2y u2 and here 2y u1 plus 2 sorry y u1 and x u2, okay, then we also see about that this one, that means represent obviously one continuous and differentiable, then f is differentiable and this one obviously continuous, okay, then these partial derivatives are also continuous here, exist and continuous here, okay, if something that means f dash is not exist, then here or exist but not continuous, then here some problem occur, okay, that means the all partial derivatives are not continuous in this case. So today we stop here.